Okay, hello everyone. Welcome to the third day of the introductory logic course. So for those who didn't join earlier, my name is Jiachen Lim, and I'll be chairing this session on behalf of Dr. Teo, the president. He's still in the midst of traveling, and I guess we understand, traveling during pandemic times is extremely complicated. But in any case, let me introduce you the speaker for today. Dr. Yuan is a postdoc fellow at the University of East Anglia, UK. He did his PhD at the University of Science and Technology of China under Qi Feng and Liu Zhenwu. His PhD thesis is about precrete-type forcings and models of ZF, and his research interest is on set theory and pure model theory. So today we begin to the first lecture by Dr. Yuan today. So yeah, I guess I can pass it on to you, Jiachen. So go ahead.
Okay, thank you very much. Thank you everyone for waiting me till so late. Yeah. Okay, I'm going to give a very general introduction into the infinities without running into details. I hope all of you can follow me. Okay, let's just pause for a moment. So I think let me begin with this. So when we were kids, when we are looking up into the night sky, we may wondering how many stars are there in the sky. So we may start count the number of the stars, 1, 2, 3. Okay, but now let's just use our imaginary power to jump out of the physical world, just continue counting process 1, 2, 3. It looks like for us, this process can go forever. So that's how we perceive the concept of infinite at the first place. So our very naive perception is that infinity is just some endless thing. Or at least it's just, as what I said, how it looks like in the first appearance. So if we just stop here, infinity is just infinity. There's no difference between them. But is that true? So, all right, indeed, there are different infinite sets. For instance, we have the set of all natural numbers, the set of all odd numbers, the set of all even numbers, and the set of all prime numbers. There are different infinite sets, but in terms of how to count them, are they really different infinities? The reality is not. They are actually the same infinity. Because you can, let's say, we can just recount the set of prime numbers exactly the same way as we count natural numbers. We say that the first prime number is 2, and the second prime number is 3, so forth. I mean, it's just depend on the way that we count them. They are just of the same cardinality, the set of all natural numbers and the set of all prime numbers. So we just wonder if the realm of infinity is just a dull, boring world. Namely, it's just a trivial. There's no difference between the infinite sets, then we can just stop here. Everything we just end this talk. But you can see the slides. There are a lot of slides afterward, so it's not the reality. Okay, the first significant observation is by Cantor. He proves that for every set, essentially, its power set is not the same as itself regarding to the number, the size of it. So here is his proof. So suppose you can enumerate the power set of A as A. So you can say, I drew a picture below. So the vertex line is just the numbers of A, the members of A. And we are going to, the horizontal line correspond to each member is just the set, which is corresponded by A. So how about the diagonal element of this diagram? So let's say B is a set so that Y is in A, but Y is not in Fy. So let's just suppose A, it's obviously a subset of A, is enumerated by F, as what we have assumed. So let's say it's Fw. So W is here. So what we can say about such a B, so let's say we ask if X is in Fw or not. So X is in Fw if and only if X is in B. By definition, X is not in F of X. So, okay, X is in Fw. All right. How about Z? So if Z is in Fz, then by definition again, Z is not in B, namely, Z is not in Fw. But there is going to be a problem when we consider the element W. So let's say whether or not W is in B. So let's suppose W is in B, then W is in F of W. But by definition, here, the definition of B, W is not in F of W, but F of W is RB. So W is not in B. So if we start with W is not in B, then the same thing, I mean, the proof just go this direction successfully again. So there is no answer to W is in B or not. So thus it's a contradiction. The contradiction comes from that B is enumerated in this diagram, so which is not possible. This gives us that the power set of A can never be enumerated as A. So there are indeed different infinities. Like for any set A, its power set will have different size of A. Okay, later on after this, so the realm of infinities is not boring, it's not dull, at least it's not trivial. But how non-trivial it is? So let's take a look at our first infinite set, the set of natural numbers. So are there any other infinities between the natural number and the power set of it? That's called the continuum hypothesis. It says there's no infinity between the countable set and the power set of the countable set. Okay, let's just move away from this a bit. So let's just go back to our counting process. So 1, 2, 3. But this time, let's just imagine our endless process just end at some point. So let's just collect all the natural numbers, the set of natural numbers. So let me call that omega. And from that omega, we keep adding successor element to it, like omega from omega on, omega plus 1, omega plus 2, etc. Then we will reach the second limit stage, which is of order type omega plus omega, or alternatively, we call that omega times 2. So forth, we can reach omega times 3, omega times 4, etc. Now we can imagine this process is not finished. So we end up somewhere, but we just take the set for granted. So we can reach without any effort to omega times omega. So let me show you if I can draw a picture to show you how this goes intuitively. So let me see. Do you know how can I draw something here? Okay, that's good. So let's just try to say how this process goes. So this is 1, and this is order type 2, and one more, 3, so forth. Okay, let me make that smaller. We don't have enough space. Okay, so this whole thing, this infinite process is going to end up with something with a limit point. Let's see here. Is it? I'm not good at this. Okay, so this is the order type omega. And from then on, you can keep adding a successor to that. So this is the first limit plus 1 element. So this is omega plus 1, plus 2, plus 3, so forth. Then the same limit exactly copy the first process. We reach the order type of omega times 2.
So you're using the dash to represent omega, right?
No, I'm just the dash is just the endless thing.
It's
so
like
the same as the
Okay, I get it. Okay, yeah.
Okay, it's just because I don't have infinite time to show you the infinite processes. You just imagine that in some time space I draw infinite many dots here.
Okay.
But we jump out of that universe, we can say the whole process. Do you get me?
Yes, yes.
So, but okay, so this is omega times 2, so forth omega times 3. But if you will the step, let me just add so let's just name the first big step as the first infinite many steps. So instead of adding one element at a time, we add omega at a time. So the same infinitary process just gives you the omega times omega, right? So you just keep going, but you keep going for infinite many times. But you can jump out of the universe again and will the whole process as a whole thing, it's omega times omega. Yeah, it's omega times omega. But this process can go forever. So you just imagine whenever you have a process, you keep going, but it will reach a limit because you can only, take finitary steps to that. But you can imagine that can go forever. But once it's finished, I mean, you just jump out of that time space. You can view the whole object. Oh, then you realize, yes, we can go to the next stage. So I don't know if you get me or not. Should I assume you are fine? Still following me?
I think it should be okay. If anyone has a question, you can let us know, or you can type it in the chat. But so far no question yet, so I think it's okay.
Okay, let me. Okay, this is trace finite counting. But we have to be careful about how to use our imaginary power, like how we jump out of the universe. Because, I mean, it's kind of paradoxical if we say that we end up with somewhere, but we just jump out of that time space to keep counting forever. But this whole thing, I mean, we are living one timeline. So there is the end of this whole thing. So where it is, it's just the strength of our axioms can tell. So the set that we are finally end up with is what we call the class ordinal numbers. But how many of them only the axioms can tell? I will show you a little bit more later about this after I just gave you the axioms. So, okay, let's just move back to the continuum hypothesis. So there is a way to restate it. So it says that there is no uncountable subset of real line with size less than continuum. So there is a standard way to view the power set of natural number as the real line. So it's just a reformulation. Oh, okay. Cantor introduced the way to analyze the subset of R by taking its limit point. So start from any set, you can run a trace finite recursive definition, inductive definition. as follows. So you start from A. At A alpha plus 1, so alpha is something that we have along this line. So A alpha plus 1 is just the limit point of A in the sense of the topology of R. And for limit gamma, for instance, R omega cross 2, omega cross 3, omega cross omega. If gamma is this cardinals, if gamma is this kind of cardinals, then you just take the intersection of all previous set. Okay, this is the operation that Cantor used to treat the sets, especially for closed sets. So if we start with a closed set, so we are going to generate a decreasing sequence of sets. Because for a closed set, its limit point is just in that set. Okay. So also A is a set. So this, I mean, you get strictly smaller and smaller sets, but it must be eventually constant because, I mean, it has a size of sets. It can never be matched up with the ordinal line, because our intuition about the set of the same size, I mean, two different set of. So I will tell you later why it's not going to be the same as the ordinal line by the axiom of replacement. So okay. So it's going to be eventually constant. Moreover, we can just take a look at the union of the sets that we are removed from the original set A. Now, remember that A is a closed set. So this set must be countable. Why? Because if X is an element of X, then X is an isolated point of exactly 1 alpha. And there is going to be a basic open set which gives you that it has the only intersection of A alpha as a singleton X. At this chi, you can map such X to the coding of the basic open set, but they are only countable, meaning basic open sets. So R is second countable, or I mean, there is a standard way to define the basic open sets. So then it will inject the set X into the set of natural numbers, and thus this set finally is countable. So are you okay with it?
Mm-hmm.
Okay, let's move on. So since X is at most countable, there must be a countable ordinal so that it's start to level off. But then if you look at such a set, it's going to be a perfect set, or namely closed, and has no isolated points. Because if it's once it has isolated points, then A gamma plus Y is not going to be the same as A gamma. That's what you say here, right? So its kernel, A gamma, is a perfect set. And the difference between the original set A and its kernel P is just the accountable set X. Okay. Let's just do a bit study on the perfect set. Despite it's a paragraph with a lot of things, but I want you to have something in mind that this process is just going to be similar to the construction of the Cantor mid-third set. So it's basically this whole paragraph is going to show that any perfect set is going to be of the same size as the continuum. So you start with the set, and you are going to build through the index on the 2 to less than omega. But you separate at each stage exactly what 1 and 2 tells you. So you build through the indices along this tree on 2 to less than omega, but you get smaller and smaller closed set. And for each of the final branch, it's going to give you an element of P, actually an element of the limit point of P, but P is closed. So for every branch of this tree, 2 to less than omega, it's going to give you an element Px in P. So this paragraph is going to give you a way to show that 2 to omega is just injective into such a P. And thus, the perfect set is always large. It's the same size as the continuum. So is everyone okay with this? Or you want me to pause for a moment, then you can read through the details. But I mean, it's just the same thing about the Cantor mid-third construction. So I just move on. So this is what Cantor has established. So for any uncountable closed subset of reals, at least, it has perfect set property. That means there's a perfect set P, which is a subset of C, so that the difference between C and P is just a countable set. And then the analog of Cantor's mid-third construction gives you that the perfect set of reals just have the same cardinality of the continuum. Okay, so that's just the Cantor reached when he was pondering his question about the size of the continuum. So his hope is that the same analysis can be generalized to all subsets of R, then we can just simply prove, it's not simple, but there is a proof for the continuum hypothesis. But the spoiler is that his hope is going to fall through because it's not provable. I'll show you within my presentation how this is going to not provable. Okay, so the spoiler tells us it's not provable. Fine. So, but wait a minute, what does that even mean? To make sense of it, we need to formalize what is a proof. So, roughly speaking, for proof, we mean a process of a wanted output, which is run by a symbolized system, which contains certain inputs called axioms, or equivalently, I mean, it can be restated in a schematic way, and they are shown by Godel to be equivalent, but the proof is highly non-trivial. So another way to say that is that we just say that for every model which satisfies the axioms must satisfy the wanted property. But we need to formalize what proof is. I'm not going to do it here. And I will assume that all of you know how to formalize the logic concept proof, the formulas, the sentences. So let's just assume everybody knows this. So I'm just going to show you the axioms of the set theory of set theory. Okay, so there are a lot of axioms, but I'm going to explain what does it mean. So the first one is called the axiom of extensionality, which says that, okay, no matter what the names for the set is, whenever they have the same member, they are the same thing. So we can formalize this sentence into the by our L epsilon language. So that says for all they, if they is in X, if only if they is in Y, then X is the same as Y. So okay, that's reasonable, right? Also, that's our intuition about sets. So the second one is that if A and B are set, then we can just collect them. That will be a set. No one will disagree with it, right? You have two objects, then you can have there is a set which contains exactly these two elements. Okay. Third one is the power of set theory, which essentially says that whenever P is a property, which is described by some formula in our L epsilon language. So for any set X, at a parameter P, the subset of X, which is decreed by the property P with parameter P for some P. I mean, if you don't have that parameter, it's also fine. So such a collection of elements in X must be accepted into our theoretic universe at its subsets of X. So Y is in if Y is just a collection of elements of X with certain properties. That's fine, right? For instance, if you have the set of all natural numbers, you accept that the set of natural numbers is in. So the set of all even numbers is just a subset defined in this way. So there exists Y plus Y is Z for Z in X. So that defines the set of even numbers. So okay, that's also reasonable. So what the fourth one is just says we can take unions. So I mean, so for every X, so X is a set of sets. So Y is the union of the elements in X. That's going to be a set. It's also reasonable, right? And the fifth one is that if X is a set, then the collection of all subset of X must be a set. Well, that's how we perceive the set should be, right? You have a set, so you just collect all of its subsets. Is it going to be a set? Yeah, I think so. At the sixth one is the axiom of replacement. So what do you mean by replacement? So let's suppose phi if is a definable function. Equivalently, if is defined by some formula again in our L epsilon language. But it guarantees that for every input there is only output. So that is what I mean, a definable function. So okay, so this axiom says if X is a set, then its replacement by such an F must be a set. Okay, let's just go back to some statements that I promised to give you some explanation after I go through, after I went through the axioms. So here, so Y A is a set, it's going to be a eventually constant. Because if it's not, it's going to be mapped somehow to the universe of the ordinal numbers, right? By replacement, we can replace it to the class of all ordinal numbers. But again, it's our universe. So we cannot, go over it. It's just where we are going to end. Since if we have a set of all ordinal numbers, then we are going to carry out the same process after it. So it's not going to be the set of all ordinal numbers, right? Okay. Then there's first large cardinal axiom. So we assume there is an infinite set. And also we assume that the universe is well-founded, namely it has a solid foundation in terms of sets. I will explain seventh and eighth condition later on. And the next one is axiom of choice. I mean, it's an equivalent way to say that, but I'd like to present it in this way because we are counting numbers. So this is actually the strongest way to state the axiom of choice, regardless of the rest of the theorems. So it says that every set is actually reorderable, or say every set is enumerable from some ordinal. But I'm not going to go into any details of axiom of choice. I'll just leave it to my colleague. Okay. So with this axioms, we can just reformulate the ordinals. We want to show that the ordinal actually exists. So historically, this was firstly done by Cantor, of course. So the philosophy behind the numbers is just we extract the similarity between two different sets with same numbers. Imagine that so what's the similarity between two apples and two watermelons? So it's a concept two. Okay, but you know, how can you present the represent the number two out of that? So our axiom just grant us powers to do that. We just collect all the sets of the same order type to represent that order type. And it's a set which we can, you know, use as a representative for the order type itself. So this is a standard way how set series work. So you can see by virtue of the axioms, let's say how to characterize two in the original way by Cantor. It's just the collection of all sets which consists of exactly two numbers. Okay, so that's the whole thing, but it doesn't give the order or any more information about the ordinals themselves. In fact, we have a better definition later on by von Neumann. So von Neumann took another approach. He found a uniform way to choose a representative of each of the class of sets. Namely, for two, yes, he chose a member of the collection of all sets of exactly two members as the representative for the number two. So his way is still in using because it's very good. I mean, the set itself also have a lot of information, so that's very convenient for using. So these ordinals are known as von Neumann ordinals. So again, we have to work with our language epsilon. So this is definition given by von Neumann. So a set is an ordinal number or ordinal. If it's a transitive set, namely for every x which is a member of the set itself, it must be a member of the set. Plus the membership relation is a will order relation of such a set. So by will ordering, we mean a relation P, which is a linear order, namely it has a trichotomy, it's a transitive, so forth, with a property that for every non-empty subset, its underlying set has a of its underlying set, so the relation has an underlying set. So the any subset of that set has a P least element. Okay, let's just move away from the abstract definition. It's actually a very concrete thing that we can work on with. So let's just try to say why this whole thing works. So first, the first one, by foundation, by the axiom of foundation, must be the empty set. So the empty set will satisfy the criteria. First of all, empty set is transitive because it doesn't have any member of it. So this is vacancy true, and also this is vacancy true. And for this one, sure, it only have one element, and there's no elements of the element of that set. So the first one is true. The second one also is vacancy true because there's only one element. And the third one, you can say the element of empty set is we don't have any member of the empty set. So the transitivity with respect to the empty set as a member of this whole set is not going to ask us to add any members into that set. How about this set? So the transitivity means that the member of that set is a member of the whole set. Okay, what the member is? The member is the empty set, but it's already in. Okay, so transitive. Okay, so the third one is transitive. How about the will ordering by the membership relation? Is it a partial order? Yes. Is it a will order? So any non-empty subset of this set has the least element under the membership relation. I think so. If it's a whole set, it's an empty set. If it contains the empty set, it's going to be the empty set. If it only contains the second component, it's just going to be it. Okay, so forth. We can carry on going. So how I construct this set? Yes, so it's just the transfinite inductive construction. Start from the empty set. You keep adding successor to it. So whenever you have an ordinal, it has a unique successor, which just takes the ordinal and union it with the singleton of itself. So this is how I construct this whole thing. And you can see from the very construction of these ordinals itself is very informative, because you can say the membership relation just gave you the well ordering. I mean, so the well ordering of that set is intrinsic. I mean, that's one of the merit of this definition. But overall, it's a very nice way to define it. Okay, so move away from this. Again, back to the slides, that how far can we go? Okay, so now we have our axioms. I'm going to show you that the first uncountable ordinal must exist as a set, namely the ordinal line so the ordinal line is not just a collection of countable sets. So we can pass through the countable universe, where the whole thing as just the element of our universe. So the first uncountable ordinal, or we call omega 1, it's not going to stop us. So we prove that omega 1 is a set from our axioms. So for that, we need some preparation, do some codings or some things within our framework. So let's say the first preparation is that for any two sets, A and B, we can construct a set which is called ordered pair. This to represent there is a pair which consists of A and B, but we can tell the order between them. So which is the first component, which is the second component. So there is a way to represent an ordered pair of A and B. So this is a set guaranteed by use our, if I remember it correctly, by our second axiom twice. Okay, we have ordered pairs. So we can use the collection of ordered pairs to formalize the relation on a given set. So whenever we have some relation on A, how we translate it into the very construction of the sets which can represent the relation? Well, it's just a collection of the ordered pairs, so which shares this property. So if X has W relation with Y, if and only if the ordered pair X and Y is in W prime. Okay, so after the tedious preparation, I can show you why omega 1 exists. So essentially, you can just take the collection of all countable well ordering for omega. So a well ordering on omega is just a relation on omega. If we code this relation in this way, so okay, the collection is then just a member of this set. Then again, by the axiom of separation, we can separate the well-ordered well-ordering out of the all subset of omega cross omega. So it must be a set. So by this definition, the set of all countable Weil ordering of this set can be replaced by the collection of countable ordinals along the von Neumann line. And thus, it's going to be an ordinal, of course, but it also has to be uncountable. Because if the collection of all countable ordinal is again a countable ordinal, then it must be in itself, which is not possible by a lot of axioms. For instance, our axiom of foundation. So the collection must be an uncountable ordinal, and it also must be the first such ordinal, because any element of it is countable. So it's the first uncountable ordinal. We call that omega 1. Okay. So that's the first observation about our ordinal line. So work with that ordinal line. We can essentially use the power set operation at the union operation to capture all of the sets in our set theoretic universe in the following way. So we start with the empty set. At successor stage, we take the power set of that set. For limit stages, we just take the union of all sets, all hierarchies that we have already got. Okay, by the virtue of our axioms, all of this, I think especially for the axiom of foundation, we can actually prove that for all x, there exists an alpha and that x is in with alpha. Okay, this hierarchy is called the cumulative hierarchy. Okay, I will just give you a brief justification of these axioms again. So if you look at our cumulative hierarchy, let's just stop at the stage omega. So what do we learn from way omega? We know that the way omega satisfies a lot of axioms. So of course it satisfies the first one. And the second one, no problem, because when you are taking power sets, you just add all of the subsets in. The third one, of course, no problem. I mean, we just assume that we've already worked in some set theoretic universe which satisfies the we are looking at way omega of that model. So the third one, yes, sure. I mean, because that's an initial segment. where omega is the initial segment of our ZFC models. Then the union, no problem. Yes, par sets, that's what we do. At replacement. Okay, because we are stuck in way omega. So, I mean, all the x's must be a finite function. But if it's a definable function, that means for every element it has only one image. So y is again must be a finite set. It's in. No problem. How about the x one? Yes, sure, no problem. 9 is also preserved. Okay. So if we have a way as a model of our ZFC axioms, then its way omega is just the model of all but the axiom of infinity. So that would mean that the existence of omega is actually increases the strength of the logical strength of the rest of axioms, because the rest of the axioms can actually prove, I mean, can interpret the piano arithmetics, then the Gauss second incompleteness for a suit. So namely, they cannot prove, so from 1 to 8, but 7 cannot prove the consistency of itself. But with the 7th, you can. So why we, I mean, all of this, all but the 7th one that we just demand there is one infinitary object to be in is, I mean, it's obvious if we are even working within the finitary universe, right? So if everything is finite, so 1 is true, right? 2, why not? 3, for a finite set, okay, we have a property. Okay, we examine 1 by 1. So which one? So for each element of the given set X, we just ask if the property holds for that element or not. Holds in, doesn't hold out. Okay, that's a very intuitive way to form a set. Why? I don't see why that set Y shouldn't be in. You take the union of the sets. Let's say we have a finite collection of sets. So each one have some members. We just take the union of that finite sets. Fine. Why? I mean, still, obviously, it should be in the power set of it. Of course. The replacement, of course. The foundation. Okay, start from the empty sets. Just go through the finitary stages. It satisfies this. Why not? The axiom of choices is vigorously true because for any finite sets we can pick without any problem. For any set, we don't have choice problem. We just pick something out of it. For 2 sets, we just first pick one element of the first set, then the one element from the second set. No problem. So So if we stay finite, everything is okay. But if we add one more thing, this whole thing is going to be more sophisticated. So why we want to make this whole thing more sophisticated? Yeah, because at least we are motivated to investigate the continuum hypothesis. At least we need to have that set in, but without adding the infinite objects outright, the rest of the axioms doesn't imply there exists one. So we have to add it in. And as what we've said, it's going to be fruitful because once we add it in, it's going to give you a very rich universe. You can imagine that omega 1 is in, omega 2 is in, so forth. It's suddenly it's going to grow quite big. How big it is? Okay, well, there is a finish line. So unfortunately, or someone views it, fortunately, the axiom doesn't imply a regular limit cardinal in the universe. So the regular means that it has the same cofinality of its size. So a cofinality function is just a cofinal function in the sense of the membership relation. So it doesn't, the regular cardinal doesn't have a order preserving function from a strictly smaller ordinal to it, cofinally to it. So our axioms doesn't imply that there is a regular limit cardinal, which we also call that weakly inaccessible cardinal. So why the implication doesn't hold? By Gödel's second incompleteness again. So if there is a regular limit cardinal, well, I mean, later on, I will just assume GCH holds. Sorry for that, but let's just assume GCH for this moment. So then kappa is a strongly inaccessible. So if kappa is a strongly inaccessible cardinal, then we do the same thing. We just cut ourselves at the stage kappa. Then we kappa is going to be a ZF model. This time we have the infinitary object omega in because kappa is inaccessible. It's way above omega. Okay. So the existence of an inaccessible cardinal just gave you the consistency of ZF or ZF plus C if your universe has C self. So it's going to be stronger than ZF C alone. So that means you cannot prove the existence of that kind of cardinals from the FC alone. Okay, that's just a brief justification of that. For later use, I'm going to mention that also that omega is also a measurable cardinal. Yeah, but not an uncountable measurable cardinal. So it has a non-principal ultra filter on it. Okay, let me just move on to the. So we finished the naive set theory part. I gave you all the axioms that I need. So let's just move forward for the independency of the continuum hypothesis. So the real processes, the real progress after Cantor's original work was carried out by Goddard in 1930s. So he just observes that despite we can't show CH is true, but it's consistently true. Or in another word, if you have a model of ZFC, he can give you a model which satisfies ZFC plus GCH based on the model that you gave to him. So there are some intuition behind which guides that construction. There are some philosophic motivation behind it, but let me just give you the simplest reason why this is. Why this could work. Okay, so the intuition behind the construction is that, so instead of allowing all the subsets of sets to get into R6 theoretic universe, he only allows the definable ones in. So in this way, the size of the power sets will be substantially reduced because we have, we rule out a lot of sets. If a set is not definable, okay, it's not good. We are not going to let it in. And the hope is that, in this way, the power set is going to be much smaller. Smaller power sets means that, there is more chance that no intermediate cardinals do exist, right? Okay, but there is a trap. I need to warn you that the consistency of the continuum hypothesis is not as simple as just the shrinking power sets. That's what I said before. Because we also need to, to still have the correct function to compute the size of the continuum. Or more specifically, if we view the continuum hypothesis as the power set of the, so if we assume AC, the real line is reorderable. The power set of the natural number is reorderable. So in this case, the continuum hypothesis is equivalent to say that the continuum is the first uncountable cardinal, right? Okay, so if we view this this question in this way, so if we eliminate too many sets during our construction, so there is a risk that we also get rid of the function that we want for the computation. I will give you some more detailed example about this argument later on. Okay. So the idea of only collecting the definable sets looks like good, it doesn't have that glitch, but it's that's because it's a nice way to define this whole thing. I think it's due to the virtue of the philosophy behind the construction. So here's the definition. Let me just tell you the set that we are going to use for the successor stages. So this is basically says the collection of the definable subsets of X, namely the set of all Y, the set of all these collections, the subset of X, which is definable by phi, but we range over all first order formulas with parameters in X. Okay, so this is the definable power set of X. So here is the definition for the constructible hierarchy. So again, we start with empty set, but you know, instead of taking the full power set in our construction of cumulative hierarchy, here we only allows all the definable subsets to get in to form the successor stage after A of alpha. And for limit ordinals, the same, just take the unions. At the constructible universe is just you know, we just take the union of all hierarchies along our ordinal line. Okay. So there is one thing that I'm going to use, but I haven't gave the definition later on, is that so this structure can be enriched by some predicate. So let's say A is a subset. I don't know. I think I can write. I hope you can follow. So fix set. So let me say the definable power set of X relative to some predicate A. The predicate is a subset of A of X. So in this scenario, we enrich the structure with one more unary predicate A. So the rest of the definition just stay the same. So A phi is the first order of formula in the L membership relation language with one more unary predicate A. At the structure we construct for the collection, we need to enrich it with an additional predicate A. That's called the relativized. So if we use the enriched definition, that's called the relativized constructible universe with one more letter, L0A, L alpha plus 1 of A, run bracket, and also L of A bracket. So you will see that later on. I'm going to use it during this talk. Okay, what can we learn from the constructible universe as we define? So first of all, we can count the size of constructible hierarchy thanks to the standard coding, which codes formulas into the natural numbers. So let me go back to the definition. So okay, so what's the size of L alpha plus 1? It's exactly the same size as L alpha because there are only countable mailing formulas as the parameters are just of the same size of L alpha. So there are only L alpha size mailing formulas which allows you to generate definable subsets. So the definable subsets of L alpha is just of the same size of L alpha. That's the first thing. The second thing is that, so by the standard coding, the formulas are coded as natural numbers. So we can define the, we can define a wheel ordering firstly by the order of the order line. So namely, the set which enters the constructable hierarchy later on always comes later in the wheel order. And within one exactly definable set, namely in L alpha plus 1 minus L alpha, all the elements can be well ordered by the formulas, because again there is a induced order by the natural numbers. So that means, as what I said, L kappa is of size kappa. Kappa is a cardinal. This is shown by induction. And secondly, L is the axiom of choice. No matter what kind of ZF model you are going to start with, if you start with a model without a choice function, then you do the same construction within that model, you are going to have a model of choice. That's how how we obtain the consistency of the axiom of choice as well. And secondly, we also note that this whole construction can be carried out within any model of ZF. In fact, much weaker system is enough. For instance, the KP should be enough. But let's just stick to the F. Since not only the formulas can be coded into natural numbers, the satisfactory relations can also be coded into subset of natural numbers. So you do the coding within a ZF model. Okay, that's all. But one more important fact is that the way to formalize this satisfaction relation, the way to define what a formula is actually very simple in the sense of logic. It's actually delta 1, 1 complicity. That means it's absolute between the F models. And hence, L is absolute. That means whenever you have an inner model M of V, L in the sense of M, namely you construct L inside M, you are going to get the same thing when you construct L in that way. So this absoluteness also gives you that L is the minimal inner model of the F. So okay. So this property is just paves the way to the following theorems called condensation. So for every limit ordinal delta, so L delta is going to satisfy enough segment of the F, which enables you. So it's a much weaker system. It's not much weaker, but it's a weaker. It could be a weaker system for the F, but that's enough for the construction of L. So for every limit ordinal delta, if M is an elementary substructure of L delta, then the transitive collapse of M is L gamma of some gamma less than or equal to delta, of course. So that's called the condensation. So with the help of that condensation lemma, so here is the theorem which will eventually gives you the GCH holds in L. So which says that if X is a subset of L alpha, then X must be accept into the constructable hierarchy before the stage of alpha plus, of course, in the sense of L. So here's the proof. So note that L is a model of axiom of choice, as what I showed you. So without loss of generality, we can assume that X is a subset of ordinal, let's say omega alpha. Fine. Okay, we just choose a limit ordinal. There is one. There is a limit ordinal delta greater than omega alpha, so that X is in, because X is in L, right? So yeah, I think here's a typo. I think should be capital letters. Okay. So okay, now take the elementary substructure of L delta so that it contains omega alpha, and X is also in that M. But by the standard Lowenheim-Skolem theorem, M is of size omega alpha without any problem. Now we are going to apply the compensation lemma to that, which shows that if we transitive collapse Rm to get N is going to be L gamma for some gamma. And again, trivially by the there is a formula which says that the universe is limit or a successor. I mean, that's trivially true that gamma must be a limit ordinal. This is implied by the elementarity that L delta is a limit ordinal. So gamma is a limit ordinal, but gamma also have to be of size strictly less than omega alpha plus, which is omega alpha plus 1. because the size of the model is of size omega alpha. Note that M is of size omega alpha. You do the stochastic collapse, it's just a bijection. But we have the omega alpha as a set which is including our M. That means the collapse function do not, do not collapse that part or say identity below that part, means that X under this collapse map is not moved. So the collapse is going to map X to X itself. And okay, so then this gives you that X is in L gamma as what we want, right? So X is in some L gamma. Gamma is less than omega alpha plus. So for any X in L omega alpha, it's going to enter the constructive hierarchy before the stage of omega alpha plus in L. So now, as a corollary, so if L is an L cardinal, again, so L thinks parset of alpha is just the union of the constructible hierarchies before the stage of alpha plus. This is what this theorem tells us. But which this union set is going to be of size alpha plus, because this alpha plus many sets of size actually alpha, as what we've seen here, right? So that means L thinks the parset of alpha is contained in some set of size alpha plus that apply to all the cardinals. So GCH essentially holds in L. Yeah, so I think I went a little bit faster than I thought to be. I don't want to enter the independence proof today. So can we finish now, or you want to go ahead?
I suppose it depends on the audience.
Or just leave the rest of I think how much time? So still 25 minutes, right?
Yeah.
So I just leave that for questions, and I'm going to give you more explanations if you want.
Okay. Yeah.
I think good. Yeah, because I think I went a little bit faster than I thought. I hope that every one of you can follow. So just time for questions.
Okay. Does anyone have any questions? Yeah, it seems like no questions so far. But I guess if there's any further questions, they can ask you again in your next session.
Okay, or do you want me to move forward? I mean, I think there's a lot of things. I mean, if you are not familiar with, say, theory, it's already a lot of new things to you. So,
yeah.
I mean,
To me, definitely yes, because I'm not a mathematician. I'm a physicist, so I'm seeing a lot of this for the first time. But for the rest in the audience, most of them should be mathematicians, I think.
So let's just stop here, and I will leave time for you to digest the thing that I talked.
Yeah. Okay. Yeah, that sounds. Yeah, I think that's fine. So okay. Yeah. Thank you, Dr. Yuan, for the nice introduction and lecture. So yeah. So I suppose that should be all for today. For administratively, I suppose the next, I should mention, the next session will be the lecture 2 for introductory model theory is on February 12th, 1 a.m. to 3 a.m. UTC. It should be 9 a.m. Malaysian time. So it's on February 12th, 1 a.m. to 3 a.m. UTC. In any case, you can check your Google Calendar that automatically converts it to your local time. So with that, I think that is all for today. So thank you very much, Jiachen, and thanks to everyone for joining. Yeah, so yeah, bye everyone. Nice to see you guys, and see you guys in the next session.
Bye, good night.
Yeah, good night. Are you in which time zone are you in now?
Yeah, I'm in UK. It's Greenwich Mean Time. So now
Okay,
it's
so
5:39 p.m. So
okay.
for me it's evening by definition, but for you it's night. Sorry for hold you on till so late.
Oh no, it's okay. Yeah, we prepared. Yeah, so it's like what 1:30 a.m. here in Malaysia. Okay, so yeah, thank you very much. Thanks again. Goodbye everyone.
Bye.